Hello, everybody, and welcome back. In this episode, we finally implement our rotational impulses. What you can see here right now is um, the last episode. We implemented the linear impulses. Well, not exactly last episode, but um, that's what our physics engine is supporting right now. Um, yeah, last time I think we calculated the inertia when I'm right. And today we're going to use this inertia and calculate the rotational impulses. And then we finally have a physics engine which all the basic, really basic features. For this, we are going to change some things. In the resolve collision, of course. And I also want to change some other things. And that's first in the material jazz, I'm going to rename bounce now to restitution. Restitution. And of course, we need to change that name in the collision manifold too. Right here. There and there. Okay, don't forget to save. Jump back to the browser, refresh and see if it's working. All right, it's still working. Awesome. And then I want to change some properties in the simulation class. And in here, I want to change the restitution of the bodies. And for this, I'm just gonna, oh yeah, and I see already I have GitHub Copilot on again, so I'm gonna disable it. All right. And here I'm gonna say, the first element, the material of the first rigid body will be changed with a restitution to, let's say, 0.25. And I'm gonna do that for the others too, but with a little bit different values. Let's say second one will be 7. This one will be 1, and the circle will be 0. Yeah. Okay. Yeah, of course I need to change this index here too. Okay, then let's jump back to the browser, see if there is a change in our bounciness. I'm not quite sure, but yeah, it looks like it. All right. Okay. I guess the second one, is this the one at the bottom? No. All right. Well, anyways, I think it looks it looks okay. Of course, the wall also has a bounce of 1. Um, I'm gonna set the restitution in. I'm gonna set the default restitution in the material to 0.5, like this. Refresh. No. Yeah, it's way better now. All right. Good. Then we can jump to the collision manifold and add our code for the rotational part. Here we need to change some things. First of all, I'm gonna move this line to the very top. There we go. Then I'm gonna calculate the linear velocity at the penetration point with respect to the angular velocity. And with this velocity, we're gonna add this velocity to the other relative velocity. And then we have like the velocity, the relative velocity of the points. You know, the shape itself is moving, but also if the shape has a rotation, then the point on a shape will have a will have a additional velocity, the rotational velocity too. So we need to add this and calculate our relative velocity from this one. So this line is not anymore valid. Yeah, but first we need to calculate the angular velocity part. And we can do this by, of course, again, declaring a variable. And I'm gonna call this one angular velocity penetration centroid A. And this is a new vector. And here we're gonna say, well, we can calculate this one by basically multiplying the angular velocity with the perpendicular vector from the body's center. All right. Yeah, from the body's centroid to the penetration point. And so we can calculate the angular velocity at the penetration point. And we also did this in the vector classes too, in the vector class too. And this is the, where is it? The get normal function. We did this right here, but in the opposite direction. Okay, the vector is pointing in the opposite direction in our case. So we're not going to use this method. Of course, we can just calculate this one with -1, but I think that would require a little bit more code. So let's do it by hand. All right, I'm going to say -1, because we're going to need the vector in the other direction. This dot Ricci A dot angular velocity times the penetration point. And I think, oh, I forgot something we need to do first. Before this one, we need to calculate the direction from the penetration point to the centroid. I totally forgot that. Well, anyways, this one is calculated like, wait a second, I'm just gonna declare this variable. So, all right, so we can calculate this one. Well, really simple. This dot penetration point subtract with Ricci A shape centroid. Okay, that's the direction vector. Important from the centroid to the penetration point. Okay, and we're gonna do that also for the other penetration point. And there we go. Okay, and now we can calculate the angular velocity at this penetration to centroid vector. All right, and here I'm going to use this variable, the penetration to centroid A, and say y. Like in the method in the vector, you know, we also did this here for the x component. We used this dot y, and for the y component we used this dot x, just flipped. And here we're gonna do it with the -1, and here with the plus x. Okay, and here I'm gonna say this dot Ricci A dot angular velocity times the penetration centroid A, but this time with the x component. And that's everything we need for this one. And of course, we need to do it for the B2. for the other shape. So I'm just gonna copy it and hope I'm not doing any errors here. Yeah, I need to change this one. I need to change this one, and I need to change this one. Okay, I think that's right. Then we can calculate the relative velocity again. So, new variable, this time I'm gonna say relative velocity A. This now is, I'm gonna call this one relative velocity. I think we can also just say velocity A, because I think that's more easier to understand, because we're not calculating here relative velocity. I'm saying velocity A instead of relative velocity, because that's the point, the velocity at the point, or the velocity the point has. Okay, so I'm gonna say here this dot Richie A dot velocity, and I'm gonna add the angular velocity from this vector here. And then I'm gonna say, well, I need to do that for the other one too. So velocity B from the right rigid body and also from the other variable. Okay. And now we can calculate the relative velocity again. I'm gonna remove this comment here. This is just this line, but this time with velocity A and velocity B. Yeah, I'm just gonna subtract here velocity B with velocity A. Okay. And then we have the relative velocity along the normal. We can still leave it like it is. Okay, cool. Yeah. Then we have the calculation. I'm gonna move the calculation of the E variable up to this line under the along normal calculation. Then we have the invert mass sum. Okay, I think we can leave it like it is. Well, no, I'm gonna make some space in here between those. It's not really necessary. I just want to have this a little bit the same like I did it in my source code. Yeah. All right, and now we calculate. Yeah, it's gonna be a bit confusing, I think. We're gonna calculate now kind of the influence of the body's rotational motion, to the collision. And we can do this by using, yeah, the cross product. I mean, a cross product, the cross product is not defined in 2D, but there's a kind of a cross product. I don't know. Yeah, we did this right here. And this value, I think you can imagine it a little bit like if you multiply this value with a vector pointing outside of your monitor. I think this is a kind of a geometric representation, but I'm not that quite sure because again it's not defined really, but yeah, I think we can just take it like it is. But yeah, it's used to calculate the rotational how did I say this? The rotational influence. Okay, so we can calculate it like this. I'm gonna do another variable p to centroid cross normal A. And this is already saying what I want to do. I want to cross the vector I did with the normal. So this dot normal. I'm gonna do this one for B2, so I'm just gonna copy that line, say B, and here I need to change this one too. Okay, then I'm gonna calculate the inverse mass of both bodies. Then I'm gonna retrieve the inertia, the invert inertia. So Ricci A invert inertia is equal to this dot Ricci A dot invert inertia. And of course the same for the other body. There we go, and there we go. And then I'm gonna calculate the cross n sum. And this is also required for the rotational part. Yeah, and this calculation, what we're doing now, basically contributes to the overall influence of the rotational movements, okay? So, of the two bodies, to the collision, let's say, dynamics. And yeah, and the inertia again is a measure of how much resistance is or how much resistance a body offers, okay, to a change in angular velocity, basically. Yeah, and we use the invert inertia to simplify some calculations. And the cross n sum now is calculated by using P to centroid normal A times P to centroid normal B times Ricci A invert inertia plus P to centroid normal B. Oh, I think I did a mistake here. This one is needed to be A. You know, we're gonna do a power of 2 calculated with the A inertia, and we're gonna do the same thing with the other one. So P to centroid no cross normal B, and then rigid body B invert inertia. Then we have the cross n sum finally. Yeah, and now I think we can leave this one like it is. Don't need to change this one, but we need to add here the cross n sum too. Just adding this one, cross n sum, alright. Then we have the impulse vector, that's right. The impulse vector for Ricci A and Ricci B. This should be fine too. Then we're gonna set the velocity. It's also fine. And then we need to add the new angular velocity we get out of the impulse. And we can do this by saying this dot Ricci A dot in angular velocity plus equals minus P to centroid cross normal A times J times Ricci A invert inertia, and the same thing for the other one, just without the minus. You know, the one of those things is going in rotating in the one direction and the other in the opposite direction, and that's why there's a minus. All right, and I hope I did everything right, because this is quite much of calculation, but I think it should work now. So let's see. Save and head back to the web browser. Refresh and just hoping that it's working. Okay, it doesn't work. Let's see why. I'm gonna take a look and I'll be back in a second. Alright, I found the error. Of course, I made this one at the really last lines, and I made a copying error. I just copied this line, edit there, and changed basically nothing. So I already changed it before before I pause the video. I just leave it like it is, but of course we need to change here Ricci A to Ricci B, then this vector, this value to B, and then the invert inertia to P to B2. Then we can save again, and then we can go back to the browser, and let's refresh, and now it should work. Let's see, and there we go. Awesome. Yeah, and now we have our rotational part of the simulation. What I want to do too is I want to change the mass of the circle. I want to change this one to, let's say, 10. Yeah, that it's gonna just that's gonna look a little bit more realistic. All right, awesome. Yeah, you can see here now, when I refresh the simulation, take a look at the circle as it's sliding on the boundary, like right now. Okay, it's sliding here when there's a contact. And what I want to do in the next episode is that we're gonna add a frictional impulse so that the circle is actually rotating. You know, it's not anymore sliding through through our world. It's now rotating through our world. Also the other bodies. Yeah, and we're gonna change a little bit our bodies again. So they're gonna slide down or kind of slide down a other kinematic body. Okay, so that's it for this episode. Yeah, I hope you got along with me, and see you in the next one. Bye bye.